For this session, we are going to discuss Wronskian Determinant, Euler's equations, and Abel's theorem. Consider an initial value problem. Second order differential equation in the following form: y double prime plus p of x y prime plus q of x y equals r of x. And then we have the initial conditions. X sub o, the value of y is y sub o, and then the first derivative at x sub o is y prime sub o. Now if p, q, and r in the standard form are continuous in an open interval containing the initial value x sub o, then there exists a unique solution y equals f of x on this interval. So, for example, consider the second order linear equation with the initial conditions: x sub squared minus 3x y double prime plus xy prime minus x plus 3y equals 0. The value of y is 2 at x equals 1, and then the value of y prime at x equals 1 is 1. So we rewrite the equation in the standard form. The first coefficient must be equal to 1. So we multiply the whole equation by 1 over x squared, or this is x times x minus 3, and then for p that will be x over this, so x will cancel out to give you 1 over x minus 3, and then for q we get negative x plus 3 over x times x minus 3. The right hand side is equal to 0, so that will be your r of x. So the only points of discontinuity for the coefficients are for p, the p of x is not defined at x equals 3, and for q the function is not defined at x equals 0 and x equals 3. Since r of x is equal to 0, it is defined for all possible values of x. So if we consider the real line, so you have the points or the singular points or the points of discontinuity. We have x equals 0, x equals 1. We will find the longest interval, okay, containing the this is 3 pala, this is 3, containing the initial point, which is x equals 1. Your x equals 1 is somewhere here. That is your x equals 1. This is from negative infinity to positive infinity. So the singular points will divide the real line into three intervals, so from negative infinity to 0, from 0 to 3, and then from 0 to positive infinity. Since x equals 1 is between 0 and 3, so we'll take the interval to be from 0, okay, from 0 to 3. So the longest interval containing the initial point x equals 1, which all the coefficients are continuous, is from 0 to 3. And therefore, the longest interval in which the previous theorem guarantees the existence of a unique solution will be from 0 to 3. Any equation in the following form is called an Euler equation. So this is a homogeneous linear equation with variable coefficients. We have x squared here, x. The solution should always be in the following form: y equals x raised to r, where r is the root of an initial equation. So for any Euler equation, this is the initial equation. We solve for the roots based on the coefficients now of y double prime, or x squared y double prime, xy prime, and then your y. So if we have now, since the initial equation is quadratic, okay, we will get two roots. Now if the two roots are distinct, then the solution will be in the following form. So c1 x raised to r1 plus c2 x raised to r2. If for double roots or identical roots, so c1 x raised to r for the second solution, that is x raised to r, then we multiply by ln of x. For complex roots, a plus or minus bi. Okay, so this is how you will present your solution. So a here will be the real root, real root, or the real number, real part, and then the imaginary part b is for the cosine and sine function. Okay, so let's have the principle of superposition. If y and y2 are solutions of the equation in the standard form, okay, second order differential equation, then the linear combination c1 y1 plus y2 c2 is a solution for all constants, c1 and c2. So for any second order differential equation, we will have this, or we will have two linearly independent solution with arbitrary constants c1 and c2. Now the question is, can all solutions can be written in this way, or do some solutions have a different form altogether? Now, to answer this question, we use the Wronskian determinant. Okay, what is a Wronskian determinant? Suppose y1 and y2 are solutions to the initial value problem. Okay, in the standard form, we have the initial value problem, the second order differential equation, and then the initial conditions. The Wronskian determinant for the solutions y1 and y2 will be defined as follows. Okay, so for the first row, you have the solutions y1, y sub 2, and then y prime, the first derivative, okay, and then for y2, the second row, you get the first derivative, no? So the first row are y1, y2, and then the second row are the first derivatives. Now it is always possible to choose constant c1, c2, so that the solution y equals c1, y1 will satisfy the differential equation and the initial conditions, if and only if the Wronskian determinant, so this is the Wronskian determinant, is not zero. This is not zero at the point x sub o. Let's have an illustration. So we find that y1 e to the negative 2 and y2 e to the negative 3 are solution to this second order linear differential equation with constant coefficients. So the auxiliary equations here are negative roots, no? Negative 2 and negative 3. And that gives you the solution e to the negative 2 and e to the negative 3. So let's get the Wronskian determinant. Okay. So this is your y1 and then your y2. We get the first derivative of e to the negative 2, that is negative 2 e to the negative 2, and then derivative of e to the negative 3 will be negative 3 e to the negative 3, and then we get the determinant. So we'll take this as positive. From right to down to the left, we'll take that as negative. So e to the negative 2 times negative 3 e to the negative 3, no? Okay, we multiply. This is e to the negative 5t. Okay, and then the other one you have positive. This is negative, so you get positive 2 here. And then e to the negative 2 times e to the negative 3, which is also e to the negative 5. So combining will give you negative e to the negative 5t. So this is your W. Okay. As you can see, W is non-zero for all values of x. The functions can be used to construct solutions of the differential equation with initial conditions at any value of x. Now let's talk about fundamental solutions. If y and y2 are solutions, okay, to the equation, okay, in the standard form, and then the solution c1 y1 plus y2 c2 with constant c1 and c2 should include every solutions to the differential equations if and only if there is a point x sub o, which is our initial value, such that your Wronskian determinant at this initial value of x is not equal to 0. It follows the two solution y1 and y2 form a fundamental set of solutions to the differential equations. Okay, so we consider the previous example, this Euler equation, and we show that the two linearly independent solutions form a fundamental set of solutions to the differential equation. So since this is an Euler equation, okay, so this will be your A2, and then your A1, and then your AO will be negative 1. Okay, and then we substitute in the auxiliary equation natin or for the initial equation. So this is your A sub 2, so we just substitute 2 here. Your A1 is 3, so substitute, and then this is minus, this is plus A sub O, which is negative 1. Okay, simplifying, so 2r squared minus 2r, and then combined with plus 3r, you get r here, positive r, and then minus 1. So this is a quadratic equation that gives negative 1 and 1/2 as the solution. So we have these two distinct roots, and for two distinct roots, this is how you write your solution. So you have two arbitrary constants c1 and c2, and then the powers negative 1 and positive 1/2. So you have two solutions. Okay, negative 1 and the other one is 1/2. Okay, so let's get the Wronskian determinant. So x1 half, we get the first derivative of x raised to negative 1/2. So bring down negative 1 and then power minus 1. So you get x raised to negative 2. And then derivative of x raised to 1/2 is 1/2. X raised to 1/2 minus 1 or negative 1/2. And then we take the determinant. So positive. This one is negative. So 1/2 x raised to negative 1/2 times x raised to negative 1 is x raised to negative 3/2. 1/2 minus 2 is negative 3/2 also. So combining, this will give you positive 3/2 x raised to negative 3/2. So as you can see, your Wronskian determinant will never be 0 for x greater than 0. Okay, so you can choose any value of x, no, and then w, the value of w will never be 0, and therefore your y1 and y2 form a fundamental set of solution for the given differential equation. 2x squared y double prime plus 3xy prime minus y equals 0 for x greater than 0. Now let's have Abel's theorem. Suppose y1 and y2 are solutions to the equation. P and Q are continuous on some open interval I. Then W is given by, so this is another way to get your Wronskian determinant using this integral definition. No? So c e to the negative integral p of x dx. P, the integral part here will be based on the coefficient of y prime, or your p. So c is a constant that depends on the two solutions y1 and y2, and definitely not on the value of x. So note that your y1, rather your w, your Wronskian, is either 0 for all x in I if c is equal to 0, and or is never 0 if I in the interval I if c is not equal to 0. Let's have an example. Okay, consider the previous example, same equation, Euler equation in particular. So the solution from the previous problem okay, so this is your y1 and y2. Okay, and we obtain from example 3, the Wronskian is 3/2 x raised to negative 3/2. So in the standard form, your P will be 3 over 2x. This is not yet in the standard form. So we multiply the whole equation by 1 over 2x squared. And we get your P as 3 over 2x. Okay, and then using the Abel's theorem, so C e raised to negative integral of p dx, no? So p is 3 over 2x. Okay, so equals c equals x raised to 3/2. This is actually e to the ln of x raised to negative 3/2. And since we have e to the ln, so that can be simplified into only x raised to negative 3/2. And The Wronskian for any pair of this is the Wronskian for any pair of fundamental solutions. So for the solutions given above, okay, we'll take C to be okay. We'll take C to be okay. 3 halves. In this particular case, it has to be positive 3 halves. Okay, so this is positive 3 halves. This is your C here. Now note that if you interchange your y1 and y2, okay, your Wronskian will be negative 3 halves x raised to negative 3. Okay, this is also correct. Now in that case, your C, if this is your solution, you change the order of your y1, y2, then you'll take C to be negative 3 halves. Okay?